Look at the sheer scale of this modern aircraft assembly floor. With millions of interconnecting parts, a single structural failure poses a catastrophic safety risk. This same logic applies to critical infrastructure. A single component failure inside a major power plant can trigger a cascading grid collapse, affecting millions. In pharmaceuticals, even a minor deviation on the assembly line compromises batch integrity. A mechanical error threatens patient safety and guarantees severe compliance violations. To cut through the noise of these massive systems, engineers use fault tree analysis, or FTA. It is a top-down, deductive method designed to trace a specific system failure backward to its exact origin. Without a rigorous, structured framework, troubleshooting in high-stakes industries relies heavily on intuition and guesswork. FTA replaces that guesswork with concrete, mathematically traceable evidence. The primary objective here is systematic discovery. An FTA maps out every possible root cause of a problem and visualizes exactly how different operational events interact to trigger a failure. Analysts also use these trees quantitatively to calculate the mathematical probability of a specific failure occurring over time. Knowing exactly how likely a breakdown is allows teams to implement highly targeted preventative actions. It identifies the weakest links in the chain so they can be reinforced, improving system reliability. FTA engineers permanent barriers, ensuring a documented failure can no longer find a path back into the production cycle. This animation represents the core architecture of an FTA diagram. It begins at the absolute peak with the top event, the singular, overarching failure you are trying to analyze. The diagram branches downward into intermediate events, the contributing causes that trigger the failure. Those intermediate steps branch out further until we hit basic events, the foundational root causes at the bottom of the tree. Organizing the problem strictly from the top down isolates the exact tier where a process deviated from its intended design. To understand how these events connect, FTA relies on logic gates. Think of these as the conditional wiring dictating how multiple causes interact. This symbol is an AND gate. Here, a higher-level failure only triggers if all the input events directly below it happen at the exact same time. But if the wiring switches to an OR gate, the rules change entirely. Now, the higher-level failure triggers if any single input event below it occurs independently. Differentiating between an AND condition and an OR condition is essential. It is the mechanism that separates discovering deep systemic flaws from writing off a mistake as an isolated human error. Let's apply this directly to a modern pharmaceutical manufacturing environment to see how the logic holds up. This chart is a complete fault tree analysis for a common production issue. Step 1 defines the top event, tablets failing a hardness test. For steps 2 and 3, the diagram branches into immediate causes, high granulation moisture and low compression pressure. Step 4 applies logic gates. The moisture branch operates under an AND gate, requiring multiple failures. The pressure branch operates under an OR gate, meaning a single sensor error triggers failure. Step 5 reveals the basic root causes, a dryer malfunction and an untrained operator. Finally, Step 6 implements CAPA, repairing the dryer and retraining staff. Applying this 6-step framework turns an ambiguous product failure into a highly specific and actionable GMP compliance directive. The primary advantage of fault tree analysis is that it provides distinct visual clarity for complex relationships. It strips away the noise and allows organizations to prioritize their risk management exactly where the data demands it. But the tool requires rigid discipline. The first major mistake teams make is defining the top event too broadly. Starting with a vague problem guarantees a bloated, unfocused investigation. There is also a real danger in overcomplicating the tree with unnecessary branches, or ignoring raw data validation for the basic events. If you plug bad data into the bottom of the tree, the whole analysis collapses. Furthermore, failing to verify your logic gate relationships inevitably leads to misidentifying the critical path, meaning your corrective actions will target the wrong root cause. An FTA is only as reliable and compliant as the precise logic governing its gates. Fault tree analysis transforms tangled operational failures into a clear, navigable logic path, exposing exactly where a system broke down. Mastering this methodology is essential for engineering effective CAPAs and guaranteeing the long-term reliability of any critical system. If you want to dive deeper into pharmaceutical root cause analysis and GMP compliance methodologies, make sure to subscribe to the channel.